We have discussed a physical application of a first-order linear differential equation, of a first-order nonlinear differential equation, and a few examples of a second-order linear differential equation. Now let's have a look at the second-order nonlinear differential equation. And a good example for this is pendulum, and we will consider pendulum as a linear oscillator or as a nonlinear oscillator. Pendulum, that means if you take a bob like that and we do not attach it to a spring so that it moves up and down, we will let it move to the side, on and on, this way. And this is called pendulum. So imagine some fixed point, and imagine some fixed length L, and imagine the bob of mass m attached to this fixed arm. We are in the gravitational field, so we have some gravity m times g, the force acting down. And this force can be decomposed into two forces. This is cancelled by this arm, and this force makes the point going back. If we describe the position by the angle phi, then the angle phi is also here and also here. So the mass times acceleration is equal to the force acting on the object. And how to relate the acceleration A with the angle phi describing the position? If we consider the length along this arc, then the distance is the phi times the radius L. Then the velocity v is the derivative of s with respect to time, or you can write it d as dt, which is L phi derivative. And the acceleration A is the derivative of the velocity, which is the second derivative of s, which is L times the second derivative of the phi. We assume L in constant and phi is a function of time. So we have MA, that means M L phi second derivative, equal to the force, and this is this component of the weight of the bob, which is mg sine of phi. And because displacement to the right results in the force to the left and vice versa, we write minus. We can divide by m, and we can divide by by L, and we arrive at the differential equation y second plus g divided by L times sine of phi is equal to 0. So this is our second order differential equation for the unknown function phi as a function of time. But here we have sine. So this equation is nonlinear. Too bad. Nonlinear equations are very difficult to solve, if at all. Sometimes we need a trick called linearization. If we assume the angle phi to be small, that means the pendulum has just a small amplitude. Then if phi is small, that means much less than 1. Then sine is approximately the argument itself. Well, you can think of this as just first order Taylor polynomial, which is quite a good approximation if phi is small. Graphically, the function sine is 0 at 0, and for small arguments, this curve is almost indistinguishable from this line, phi itself. So under this assumption, we can use this simplification called linearization, and then this nonlinear differential equation turns to a linear one. And instead of sine phi, we just write phi alone. And this is a linear differential equation. And we already know that this has the meaning of the frequency, of the square of the frequency. And we have again sine omega t, cosine omega t, the undamped oscillator. So we can write that phi is some constant times cosine of omega 0 t, and then phi derivative is minus c1 omega 0 sine omega 0 t. So if we sketch the situation in the plane where we plot phi and phi derivative, then phi plotted along the horizontal axis is some kind of x, and y derivative plotted along the vertical axis, y coordinate, cosine t, sine t. This is the equation of the circle. Well, not exactly, some constant is here, so some ellipse, but up to some deformation. This is a round object like ellipse or circle. This minus means that the ellipse is not run in the positive direction, but rather in the negative direction. So for small x, we have ellipses like that. The origin itself is also a possible solution. If the constants are 0, phi is 0, phi derivative is 0, and that means the pendulum is in the bottom equilibrium position at rest, no oscillation, no motion. Also note that if we are above the horizontal axis, then phi derivative is positive, and positive derivative means increasing phi. So we move to the right if we are up, and here the phi derivative is negative, so negative derivative means decreasing phi, so we move to the left, to the right, to the left, and these circles describe the motion. The small circle describes the motion with a small amplitude, and the larger circle describes the motion with a larger amplitude. For the linear equation, there would be an infinite system of circles or ellipses like that, small circles, large circles, everything possible. But if we go back to the nonlinear equation, then the pendulum with large amplitude has also the upper position when phi is pi, or phi is minus pi. And between these two positions, there is a motion that looks like that. Going down and going back up, and approximately to the same position. And this corresponds to a trajectory like that, going from minus pi to pi, and then once again going back. Well, and here in between we have a system of circles like, oh, not circles, closed trajectories like that. But as phi appears as an argument of sine, which is periodic, then phi is pi is equivalent to phi is 3 pi. And again, we have these trajectories like before. And the bottom equilibrium point, phi is 0, is equivalent to phi is 2 pi. So the same picture around 0 must be also around the point 2 pi 0. Well, and similar for minus pi and minus 2 pi. But such a pendulum allows another type of motion. If you kick the pendulum fast enough, then it will rotate like that. It moves quickly near the bottom point and slowly near the upper point, but it goes this way. And this can be visualized here by a trajectory like that. Rotating in the, say, positive direction, and then instead of going this way, we can also go this way. And this corresponds to curves like that. So this is called a phase portrait of this system with coordinates phi and phi derivative. And each curve, each trajectory corresponds to one possible motion, to one possible time evolution of the system. And this part of mathematics is called dynamical systems theory, and it is a very nice, very practical, fascinating, interesting part of modern mathematics.